Hello. Hello? How about now? Okay, a little bit better, but worse audio quality. Okay, that's better. All right, fantastic. I guess this is just a thing now. Uh, Luckily, nobody's here to see me fumble horrifically. I doubt that's true. Oh, wow, there are four people here. Or nobody? I have no ideas. Hey, Nagel! Silver Sword Day? Wow, I'm assuming this is coming through on your end. I'm sorry for that. Currently just trying to fix the audio issues. They don't seem... This doesn't seem to be good. No, 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 that's it for me too. Sorry. What if I don't know what to do? Oh no, I don't know what I just did. Hello. Is this a little bit better? All right. How about now? Ah, okay. So the issue is my noise canceling source, which is a major issue. I mean, as you guys can hear, there is a kind of fan going on in the background. Yeah. Has that doubled audio? What's going on with that? And that has this undoubled the audio. Hey, I think I fixed it. Is that coming through on your guys' end? Fantastic. I literally just turned off the pulse audio and went to mic slash audio. I don't know what I did there. To be entirely honest, that's strange. Anyway, hi everybody. I'm very happy to see all of you. Well, the three of you are here. That's exciting to see. Welcome, Nagel. I don't think we saw you last time, which is fine, of course. Anyway, I think we're going to get started quite quickly. We did only get through half of the first one, which is an absolute shame, but nothing we can do about it. Here we go. That's GitHub. Is it here? Ah, wow. No, it's not. I have no idea which button this is. Once again, I am massively incompetent. Not a problem, Nagel. I am happy to see you again, and so sorry for not being more active on the Lemmy. I wish I could be. I'm honestly surprised I'm here currently. How do I pop this thing out? I'm glad that you all every single time get to see my massive amounts of incompetence. It's a very fun thing. Normally that's just a me thing. Normally only I have to deal with that. Heck yeah. Why are some people red and others not red? I don't. Okay. That's a strange thing, but mysteries in life are plentiful, I guess. Anyway, I guess we should talk about what we did yesterday. Or a week ago. My god. Right, last week we got to this section of the book, we fumbled through this all the way to through the first, what is ownership, and most of, references and borrowing. I believe Keith was going to learn a bit more on his own. I don't know where exactly we left off, so I'm going to read randomly through it, see if I can remember some of this stuff. I will admit I have very little time for learning on my own. This 2 hour period I've carved out for myself is about what we've got. But I think it's really cool. Borrowing is basically a structure of a person being able to pass, or sorry, it's this idea that a variable owns a specific thing, and when you pass a variable by reference to another one, it no longer has ownership and thus cannot be read to. One question I have, a major question, is once that's been passed and it's no longer usable, why is it not an error to still have it around, still have it working? Why does it not just get deleted? What uses are there for it? But I guess that's something we'll learn eventually. Have any of you got any thoughts? Have you guys done any further reading on this as I've been gone? You guys still enjoying Rust? Honestly, I quite like it. I think it's quite cool. I'm going to wait a moment while I read randomly. I believe that it might be here, actually, that we are. Rust avoids. Yeah. Oh, so you've been reading on your own? Yeah. Honestly, that's the best way to do it. Sleep on it a few days, reread, restructure, try working with it. A lot of times for myself, I'll read through a lot, not really get it, or think that I get it. Then I'll work with it and actually understand what I'm doing. But still, I love the concept. Fair enough, Keith. Okay. Yeah, you've skimmed the book. Probably read parts again for sure, especially after you've tried doing things. Thus, challenge in life. Yeah, I really want to do that challenge. I keep saying every time we do this that I'm going to go on Thursday and I'm going to do some coding with this. I'm going to code, I'm going to code, I'm going to code. But every time on Thursday, just something comes up. Awful situation. I love how I'm slowly fading out of existence. I love that. That's great. Uh, anyway, unless there's anybody who wants to talk about something specific, maybe their life, I don't know. No, that's boring, man. Rust is our life now. But unless anybody wants to talk about anything else, I'm just gonna get started. Gonna start reading from Rust Avoids Simultaneous Alias and Mutation. You went to the boxing gym and got hit in the face? Why did you do that? Why would you do that to yourself? That sounds terrifying. Can I join it? Are you like a normal boxer? I'm sorry, I got a sidetrack on that. That's really interesting. Is this like a normal thing? I've always wanted to learn a martial art, and honestly, boxing seems like a cool idea. The progression sport for fitness. I don't know what that means, to be honest. Are you okay though, Keith? No, you're not okay, I guess, is the falling of events. I'm sorry you got hit in the face, though. Oh, has a good feedback for improving. I guess it would, honestly. Get hit in the face less. You feel less tired afterwards. You get less hit in. Yeah. Some people are just into getting hit in the face, honestly. And you know what? More power to them. That is really cool, though. I wish I could get into boxing, man, but I'm a lazy fat piece of rust code, I guess. Uh, I've said this before, I'll say it again. I love you, Keith. You are my favorite man. Anyway, I'm just gonna get started. Oh, I'm literally in the middle of nowhere, so it takes like half an hour to get into town. The only sport that requires you to go against your instinct? I wouldn't know much about that. Now I kind of want to learn about boxing. If only I had time for that, but that is really interesting. I've never seen $1 million baby though. Huh. Well, again, I'm going to get started with Rust avoids simultaneous aliasing and mutations. Forces are a powerful and dangerous feature because they enable aliasing. Aliasing is accessing the same data through different variables. On its own, aliasing is harmless, but combined with mutation, we have a recipe for disaster. One variable can pull the rug out from another variable in many ways. For example, by deallocating the alias data, leaving the other variable to point to deallocated memory, by mutating the alias data, invalidating runtime properties expected by the other variable, by concurrently mutating the alias data, causing a data race with non-deterministic behavior for the other variable. As a running example, we are going to look at a program using the vector. I think we've seen this before. I believe we've read through this. Data structure vec. Unlike array, which has a fixed length, vectors have a variable length by storing their elements in the heap. For example, vec push adds an element to the end of the vector like this. I believe we have read this. Does anybody know where we stop? I don't. Let's just continue reading through. We're halfway through anyway. The macro vec creates a vector with the elements between the brackets. The vector v has type vec I32. The syntax I32 means the elements of the vector have type I32. Apologies, I'm going to have to go turn that off. Okay. I am back. Right. One important implementation detail is that V allocates a heap memory array of a certain capacity. We can peek into vec's internals and see this detail for ourselves. Let mut V of type vector I32 equal vector containing 1, 2, and 3. This is point 1. At point 1, location 1, we have the stack, which holds main, with the frame main variable v holding a variable of type. Okay, that is very complicated, and I have stopped gaining knowledge here. Okay. Note, click on the binocular icon at the top right of the diagram to toggle its detail view in any runtime diagram. Okay. That's a lot simpler, okay? We have a variable called v, which points to the heap memory 1, 2, 3. That's great. I don't know what any of that is. Anyway, length here, I guess. I guess this is a vector with a buffer type, which holds a raw vec, which as well as capacity. Sorry, a raw vec, which holds pointer and capacity. A pointer of type unique. The pointer is a unique type. Seems similar to C++ vector? Yeah, seems exactly the same, but I've never seen it broken down like this. That's cool to see, I guess. Let's move on now. Notice that the vector has a length, len, of 3, and a capacity, cap, of 3. The vector is at capacity, so when we do a push, the vector has to create a new allocation with larger capacity. Copy all of the elements over and deallocate the original heap array. The diagram above, the array 1, 2, 3, 4 is in a potentially different memory location than the original array 1, 2, 3. To tie this back to memory safety, let's bring references into the mix. Say we created a reference to a vector's heap data. Then that reference can be invalidated by a push, as simulated below. We have mutable vector of I32, let num redirection. Sorry, a reference of I32 equal redirect, or sorry, the reference of the element 2, that'll be 3, v dot push 4. Third element is trying to get num. Okay, that's going to fail because the tree has changed positions. Okay, at location 1 we have v and num going in, with v referencing the entirety of this, with num referencing solely the third one. Location 2, while we push it, we have v hitting 1, 2, and 3. Num is a dead pointer. And when we try and use num, of course, since it's a dead pointer, it is it's a failure. That is an error. Of course, it does not error out just because there is a dead pointer, as we have learned before. Initially, v points to an array with 3 elements on the heap. Then num is created as a reference to the third element, as seen in location 1. However, the operation v.push4 resizes v. The resize will deallocate the previous array and allocate a new, bigger array. In the process, num is left pointing to an invalid memory location. Therefore, at L3, dereferencing num reads invalid memory, causing undefined behavior. In more abstract terms, the issue is that the vector v is both aliased by the reference num and mutated by the operation v.push4. So to avoid these kinds of issues, Rust follows a basic principle. Pointer safety principle. Data should never be aliased and mutated at the same time. Okay. Data can be aliased. Data can be mutated. But data cannot be both aliased and mutated. For example, Rust enforces this principle for boxes, owned pointers, by disallowing aliasing. Assigning a box from one variable to another will move ownership, invalidating the previous variable. Owned data can only be accessed by the owner, no aliases. However, because references are non-owning pointers, they need different rules than boxes to ensure the pointer safety principle. By design, references are meant to temporarily create aliases. In the rest of this section, we will explain the basics of how Rust ensures the safety of references through the borrow checker. References change permissions on paths. The core idea behind the borrow checker is that variables have 3 kinds of permissions on their data: read, write, and own. Readable data. Read is data. Data can be copied from another location. Write, data can be mutated in place. Own, data can be moved or dropped. These permissions don't exist at runtime, only within the compiler. They describe how the compiler thinks about your program before the program is executed. By default, a variable has read/own permissions on its data. It is not mutable. You must use the keyword. If a variable is annotated with let mute, then it also has the write permission. The key idea is that references can temporarily remove these permissions. Okay. To illustrate this idea, let's look at the permission on a variation of the program above that is actually safe. The push has been moved after the print line. The permissions in this program are visualized with a new kind of diagram. The diagram shows the changes in permissions on each line. I wonder if we can have a plugin that just shows this in NeoVim or whatever. Just to have track of this. We have let mute v vec I32 equal to vector with read, write, and ownership permissions. Then, when we reference num, v no longer has write or ownership permissions. V no longer has write or ownership permissions. Okay, yeah, because if we change num, that's fine, because it now owns the entire vector, I guess. I guess it owns the entire vector. Yeah, that's true. So, but num has read and ownership rights. Does it have that to the entire? Well, I mean, you can't access any of the vector but the last one. I understand that. Why doesn't it just have the final one? But this is good to know. This is good to know. When we take a reference of a part of an object, or well, I guess it's not really an object, some struct, it will lose us ownership rights over the entire thing. And then the reference of num has read. Yep, that's what I'm saying. V no longer has ownership. Num has ownership. When you take a reference to a part of a vector or other struct, the parent vector or other struct loses ownership, and the only ownership is with num. No, you can't access the whole vector. Nothing owns the whole vector anymore at this point. Good point, though, Megal. Yeah. And okay. Print line. Third element is, and we dereference num to get the value. It loses read value, loses read and ownership value, and is reverted to v, to the vector. Okay, so at the last point where it is used, it exits, probably doesn't exit memory, but it reverts ownership, so we can push. I see. That must have been hell to write. That must have been very difficult to write as a compiler. Let's walk through each line. After let v equals, the variable v has been the variable v has been initialized, indicated by that symbol, which pushes up. It gains R, W, and O functions, read, write, and ownership. The plus sign indicates gain. After let num equals reference v 2, the data in v has been borrowed by num, indicated by the arrow icon. 3 things happen. The borrow removes read and write permissions from v. The slash indicates loss. V cannot be owned, written, or owned, but it can still be read. There. The variable num has gained the read and ownership permissions. Num is not writable. The missing W permission is shown as a dash because it was not marked let mute. So it can be mutable, but it is not in this case. The path, dereference num, has gained the read permission. After print line, then num is no longer in use, so v is no longer borrowed. Therefore, v regains its write and ownership permissions, indicated by the reversion symbol. Num and reference num have lost all of their permissions, indicated by the downward symbol. After v.push4, then v is no longer in use and loses all of its permissions. Okay. Next, let's explore a few nuances of the diagram. First, why do we see both num and reference num, dereference num? Because it's different to access data through a reference versus to manipulate that reference itself. For example, say we declared a reference to a number with let mut. Let x equal 0. X, that symbol is the gain, I guess. Or initialization, I guess. Apologies. Gains it with read and ownership, but not right because it's not mute. Let x underscore ref equal the reference to x. It is mutable. X loses ownership. X underscore ref gains ownership and write. And the reference and the dereference of x underscore ref is initialized with the read permissions, but not the write or ownership. Notice that x underscore ref has the W permission, while dereference x underscore ref does not. That means that we can assign x underscore ref to a different reference, e.g. x underscore ref equals a dereference of y, a reference of y, but we cannot mutate the pointed data. Okay, e.g. dereference x underscore ref plus equals 1. Okay. That is interesting. I didn't get that originally. I'm glad that it explained. So we can't actually change the value. Here we have 1, 2, 3, and then we have num, which is just 3. We can't make that 17. That can't be changed to 17 at any point in time. In order to change that, we would have to create a new object and change what that is referencing itself. We would have to create a new literal. Changing that would be difficult. Why, though? Okay? Why? More generally, permissions are defined on paths and not just variables. A path is anything you can put to the left-hand side of an assignment. Paths include variables like a, dereferences of paths like dereference a, array accesses of paths like a item 0, fields of paths like a dot 0 for tuples or a dot field for structs, discussed in next chapter. Any combination of the above, like the dereferencing of a item 0 member 1. That I hate this. I'll never not hate this structure, but I can understand why it's there. I just wish that people could make it more readable. Second, why do paths lose permissions when they become unused? Because some permissions are mutually exclusive. If num equals or sadomasochism. Sadomasochist. Whoever put that word into existence, sadomasochist. Right. Then, if num equals the reference of v 2, then v cannot be mutated or dropped while num is in use. But that doesn't mean it's invalid to use num for more time. For example, if we add another print to the above program, then num simply loses its permissions later. Okay, yeah, that's fair. And this is just explaining how if you use it again, it keeps its permission for longer. It just uses it until it's not used. The borrow checker finds permission violation. Recall the pointer safety principle. Data should not be aliased and mutated. The goal of these permissions is to ensure that data cannot be mutated if it is aliased. Creating a reference to data, borrowing it, causes that data to be temporarily read-only until the reference is no longer used. Rust uses these permissions in its borrow checker. The borrow checker looks for potentially unsafe operations involving references. Let's return to the unsafe program we saw earlier, where push invalidates a reference. This time we'll add another aspect to the permissions diagram. Right, we have let mute v equals v of type vec I32 equals vector. We have initialize with read write ownership. We have let num type I32 reference equal reference the R symbol. What the fuck is going on here? Are we supposed to put emojis in our data? Enter code? Oh, okay, so what it's doing apparently is v now loses write and ownership. Num is initialized with read and ownership, as is normal. And of course, this reference is only readable. What the fuck? I don't know. Okay, sure. Anytime a path is used, Rust expects that path to have certain permissions, depending on the operation. For example, the borrow reference v2 requires that v is readable. Therefore, the R permission is shown between the operation, reference, and the path v. The letter is filled in because v has the read permission at that line. Okay. To be honest, I don't understand what it's saying. I'm just going to reread it quite quickly. Anytime a path is used, Rust expects that path to have certain permissions depending on the operation. For example, the borrow reference v of 2 requires that v is readable. Therefore, the read permission is shown between the operation and the path v. The letter is filled in because v has the read permission at that line. Is that just telling us where it gains that permission? I don't understand. I hope that's all they're doing. That's ugly as hell, but I can understand why. It's more complex. I'm just going to move forward with the understanding that's what they're trying to do. By contrast, the mutating operation v.push4 requires that v is readable and writable. Like whenever an operation happens, they just want to show the state of ownership. Okay, but what are they talking about with it being filled in or not? What does that mean? Is that just trying to show that it does not have right ownership? Just like, hey, this doesn't have right ownership? Because it doesn't. Because it does. Okay. I guess so, yeah, I guess. Yeah, why didn't they just introduce it? Okay, that's just an incredibly confusing way of doing this, in my personal opinion. Thank you, though. Well, I guess we'll just move forward with that assumption. By contrast, the mutating operation v.push requires that v is readable and writable. Both r and w are shown. However, v does not have write permission. It is borrowed from num. For the letter, w is hollow, indicating that the write permission is expected, but v does not have it. Okay, this is... yeah. Yeah. And DSL? What does dick-sucking lips have to do with this? Anyway, sorry. Let's be professional, guys. Anyway, yeah, I guess that literally is what it is. That's what they're doing. And I'm just an actual moron. Domain-specific language. Thank you. If you try and compile this program, the Rust compiler will return the following error. Cannot borrow v as mutable, because it is also borrowed as immutable. Let num reference I32 equal reference v2. Immutable borrow occurs here. I love the error in Rust. Seriously. Look at this. It's just like, here's exactly where the mutable borrow occurs. Here's where you are borrowing it from. Here is where you're using it. It tells you everywhere where you messed up, man. I love this. The error message explains that v cannot be mutated while the reference num is in use. That's the surface level reason. The underlying issue is that num could be invalidated by push. Rust catches that potential violation in memory safety. Good stuff. Mutable references provide unique and non-owning access to data. The references we have seen so far are read-only immutable references, also called shared references. Immutable references permit aliasing but disallow mutation. However, it is also useful to temporarily provide mutable access to data without moving it. The mechanism for this mutable reference, also called unique references, the mechanism for this is mutable references, also called unique references. Here's a simple example of a mutable reference with the accompanying permissions change. Let mute v vec of type I32 equal vec123. Let num, a reference to immutable I32, equal a reference to mute v. And now they've changed it again. I love how they've got 3 different types here, and we have this beautiful little... They don't know a lot about CSS, but I think they're trying, guys. Reference to immutable v2. At the first, we have read, write, ownership. V loses read, write, and ownership. Num gains read and ownership but not right. You cannot change where you cannot change where this is referencing towards, and the dereference of num gains write and read. Fantastic. Reference of num plus equals 1. Third element is readable, dereference num. The regains write, read, and ownership. Num and reference num lose all permissions. Current line vector is now, and the vector with a read permission. What? I don't know what it's doing here. It's just reading the entire vector, I guess. I don't know what this is. Does this just print out the entirety of the vector? But yeah, afterwards, I guess this is pointing afterwards. Afterwards, it loses all permissions due to the fact that it is no longer in use. Note that when the expected permissions are not strictly relevant to an example, we will abbreviate them as dots like this. Thank you for that. You can hover your mouse over the circles or tap on the touchscreen to see the corresponding permission letters. Thank you for that. Colorblind people rejoice. A mutable reference is created when reference mute operator. A mutable reference is created with the reference mute operator. The type of num is written as reference mute I32. Compared to immutable references, you can see two important differences in the permissions. When num was an immutable reference, v still had the R permission. Now that num is a mutable reference, v has lost all permissions while num is in use. Can't even read it. Race conditions, that's why. When num was an immutable reference, the path dereference num only had the read operator. Now that num is a mutable reference, dereference num has also gained the write permission. The first observation is what makes mutable references safe. Mutable references allow mutation but prevent aliasing. The borrowed path v becomes temporarily unusable, though effectively not an alias. The second observation is what makes mutable references useful. V, too, can be mutated through reference num, dereference num. For example, dereference num plus equals 1 mutates v, too. Note that dereference num has the write permission, but num does not. Num refers to the mutable reference itself. E.g., num cannot be reassigned to a different mutable reference. Mutable references can also be temporarily downgraded to read-only references. For example, here, where we have num of type reference to a mutable I32 equals reference mutable v2, where num is initialized with read and write permissions. Apparently there is more, which does not matter. Let num2 equal reference to a mutable I32. Okay, yeah, mutable references can be re-referenced, I guess. I32 equals the reference of the dereference num. Num, dereference num gains has read, loses write. Reference num2 gains read. No write, no ownership. Ownership is still with v, I guess? No, ownership is with num. What? Oh, yeah, ownership is still with num? No, you moron. Ownership is with num2. Of course it is. The dereferencing of num2 does not have ownership, but num2 itself does have ownership. Right. And we can print the dereferencing of num and the dereferencing of num2. Perfectly fine because both have read. Note, when permission changes are not relevant. Yep. Oh, yeah. When permission changes are not relevant, we'll hide them. You can view the steps by clicking. Yeah, I think we understand that. In this program, the borrow reference to a dereferenced num removes the write permission from dereferenced num, but not the read permission. So, print line can both can read both the dereference of num and dereference num2. Permissions are returned at the end of a reference's lifetime. Okay, we said above that a reference changes permissions while it is in use. The phrase in use is describing a reference's lifetime, or the range of code spanning from its birth, where the reference is created, to its death, the last times the reference is used. For example, this program, the lifetime of y, starts with let y equal reference x, and ends with let z equal the dereference of y. So, y is initialized here, that is where it starts, its life, and then it dies after it is no longer used. Fantastic. Z dies here, I guess, if there's no more code. The write permission on x is returned to x after the lifetime of y has ended, like we have seen before. Why didn't you just use the word lifetime from the start, from the get-go, instead of in use? Like, it's not a hard thing to explain. I guess, like, since it's something you're going to use a lot, you want to explain it specifically. But I mean, you could have done both. In the previous example, a lifetime has been a lifetime has been a contiguous region of code. However, once we introduce control flow, this is not necessarily the case. For example, here's a function that capitalizes the first character in a vector of ASCII characters. A function, ASCII capitalize, taking in v of mutable reference to a vector of type char. Let c equals the reference of the first element. If c is ASCII lowercase, let up equal c dot to underscore ASCII dot underscore uppercase. V of type 0 equals up. Oh, okay, so yeah, we are creating up, which is just C, our character, and then uppercase the character, just change it to a new character, and then allow D0 equal up. D is dead at this point. Print line, already capitalized, print out the entirety of V, which will be the entire string, I guess. The variable C has a different lifetime in each branch of the if statement. In the then blocks, and in the then block, C is used in the expression C.to underscore ASCII underscore uppercase. Therefore, the reference of V does not regain the write permission until after that line. However, in the else block, C is not used. Dereferenced V immediately regains the write permission on entry to the else block. Now that is an else block, I'm an idiot. Yep, if it is successful, C is used. If it is unsuccessful, C is unused, meaning that C will have never actually had a life. It would have began and died right here, same time. Okay. How can you do that not in runtime if it's using a runtime if statement? Yeah, because if it's in runtime, if there's an if statement which requires some check within lifetime, I guess C would lose its variable at the time in which C was defined, not hit the if statement, but you can't do that via compilation. How does the borrow checker work in that situation? I don't understand that, actually. Well, I guess we'll see if we start coding something quite complex. The variable C has a different lifetime. Yep, we've already read that. And let's start this quiz. I love these quizzes. Consider the permissions of the following program. Let mute s equals string from hello, read, write, and ownership. Let t equals reference mute s. Read, write, ownership is dead. Sorry, no longer has read, write, and ownership. T and t reference have read. T reference has write, but t is ownership. Here, t dot push string space world. S regains read, write, and ownership. T no longer has read or ownership. Reference T no longer has read or write. We print S in its entirety, it loses all permissions. At the point marked here, what are the permissions on the path S? On the path S. The reference to S, I don't think it's specifically stated. If this has no read, write, or I believe that would have no permissions, correct? Is anybody going to say anything different from this point? Yeah, because if this doesn't have any of those, I don't see how the reference could have anything there. Yeah, makes sense to me. Submit query. Consider the permissions on the following program. We have a function, get first. We have a variable, which is a reference of v. We have, let's just read what it is. Which of the following explains why strings loses and regains write permissions? Okay, so I guess let's read through this entirely. Let mute strings equal vector of type with equals a vector that is filled with strings from capital A, strings from capital B. So that would be AB, I guess. I don't exactly know what that would do. That would be a vector with a strings from A and a strings from B. So that would be a vector with the literal A and B, but they're type strings, I guess. Let first equal get first, which is a reference to strings. Read, sorry. Strings loses right and ownership. First gains ownership, does not have right. The reference only has read because this is not a mutable borrow. If first, right, read dot length is greater than 0, strings regains everything. Sorry, strings dot push strings colon from C. Okay. So strings loses and regains write permission. Yes, if it's bigger than 0, we are pushing, and it has write permission at this point in time because first is no longer used at this point. First no longer is used after this point, and thus strings regains permission. Strings does not need write permission until strings.push operation, so it only regains write permission at that statement. That's incorrect. Because first refers to strings, and strings can only be mutated within a nested scope like the if statement. Get underscore first returns an immutable reference to data within strings. So strings is not writable while first is live. I believe that is correct. Strings is not writable while the immutable reference strings is passed to get underscore first is live. Sorry, passed to get underscore first is live. I believe that this is the correct one because this does return. Again, I will never get used to this. Just put a return statement. How hard is that? Because this will return a reference to the passed in vector, which is a reference to strings. Fantastic. Since it returns that, that has ownership till the point in which it dies. Sorry, no, it will only have ownership within the context of this. Once it is returned, the reference is returned. Thus, first gains ownership until ownership of first is dead. Until it is no longer used, thus ownership is passed back to strings. Okay, I believe that's correct. Consider this unsafe program. v1 equals vector 123. Let mute v2 equal v1. v2 dot push for front line printing v1 0. Which of the following best describes the point at which undefined behavior occurs within this program? I believe it would be at use, because it's perfectly fine to have a reference, to have a variable which references unmarked data, or sorry, data which is has been moved or has been freed or no longer, or has been moved from its current state in memory. That's fine. So I believe it's only at read, location 1, where this actually fails. Undefined behavior occurs only here? Wait, let's look at ownership. Let v1 equal vec. Let mute v2 equal v1. v2 now has ownership, I believe. v2 dot push 4. That's fine, because v2 has ownership, but is that mutable ownership? Is that a mutable reference? I think that's fine. Huh. Unless anybody wants to argue for line 3, I believe it's line 4, but I could see line 3 due to the fact that this is not a mutable reference. You're in line 3? I think line 3 makes a lot of sense, actually. I think this is a bit of a gotcha here. I am personally leaning to line 4, but line 3, I believe, is a strong contender. Right, let's read the responses. Maybe they'll accidentally tell us. v10 reads v1, which points to deallocated memory. That is what we believe, or me and Sorbet believe. v1 has been moved into v2 on line 2. That's fine. I see no issue with that. v1 has its pointer invalidated by the push on line 3. That is correct, and that's what Magel believes is the problem. Oh, no, you believe this one. v2 owns the vector data on the heap, while v1 does not. Good. You go with option 3? I believe you would. But I believe this is also true. v2 owns the vector data on the heap, while v1 does not. At this point, that is correct. That's what personally I believe is the issue. I'm going to go with that, but Nagel, I think you might be right. But it also does point to deallocated memory. I'm not sure that couts as that counts as undefined though. Technically 4 and 1 are correct, right? Yeah, that's what I'm saying, Sorbet. I believe that is undefined behavior, because this is trying to get v1, which A, does not have ownership, and B, is deallocated memory. That's some random garbage. That's actually the use after move or use after free error. So if we try and access v1 after it has been moved, I'm pointing towards 4, to be honest. No, I believe 1. 1 is where it first goes wrong. But 4, I believe, is also correct. But I also believe you could be right on your original with 3. So let's go. We got this one correct. Hooray. Got this one correct. Hooray. We got this one correct. Okay. Fantastic. Wow, honestly, I was concerned. Without you guys, I may have picked 4. I feel a lot smarter now. Thank you, guys. Context. Let's get the context. The undefined behavior arises because v1 is read after being freed. Note that the other three options are correct statements about the program, but they do not explain why the undefined behavior actually occurs. For example, if the print line were deleted, then the other three options are still true, but the program no longer has undefined behavior. Good to know. That's why it's kind of messing with us, because all these are correct answers. Just one of them is undefined, the rest are not. I guess so. Data must outlive all of its references. That was a good question. I entirely agree. Yeah. I really like this book. Brown.edu. Brown, the School of Brown, is really, this is really well made. Unless this is originally from the Rust team, at which point, congratulations to the Rust team. That's fantastic. Don't know which part is theirs and which part isn't, but I guess that's kind of on purpose. Data must outlive all of its references. As a part of the pointer safety principle, the borrow checker enforces that data must outlive any references to it. Rust enforces this property in two ways. First way deals with references that are created and dropped within the scope of a single function. For example, say we try to drop a string while holding a reference to it. We have a string, hello world, let s underscore reference, which is a reference of s, drop the drop s. Can we see anything? What? I don't know, man. Anyway, drop s, print line, s underscore ref. I don't actually know what it's trying to say here. As a part of pointer safety principle, the borrow checker enforces that data must outlive any references to it. Rust enforces the property in two ways. The first way deals with references that are created and dropped within the scope of a single function. For example, say we try and drop a string while holding a reference to it. Okay, so yes, we are trying to drop a string, but there's still a reference which is alive. But the borrow checker, it doesn't own it, so it can't drop it, I guess. Yeah, that makes sense. To catch these kinds of error, Rust uses the permissions we've already discussed. The borrow of reference s removes the ownership permissions from s. However, drop expects the ownership permission, leading to a permission mismatch. I can see myself thinking in a different structure than this is trying to lead me towards. Think of these as like permissions on a Linux file system, which really kind of is what it's like, but not entirely. I feel myself being pulled in two directions here, and I don't believe I am currently going to grasp the second one, which is the one which is true. That was meaningless dribble. Okay. The key idea is that in this example, Rust knows how long s underscore rev lives. But Rust needs a different enforcement mechanism when it doesn't know how long a reference lives. Specifically, when references are either input to a function or output from a function. For example, here's a say function that returns a reference to the first element in a vector. I was asking about this before. You agree, Magel? I don't know. I don't know if I, sorry, I'm incredibly tired. My communication abilities are very low. I'm glad that I have somebody who thinks the same as me. Thank you, Magel. Here's a say function that returns a reference to the first element in a vector. A function first string of vector returns a string reference. Let s underscore ref equal reference to strings 0. And then return s underscore ref. You just put the word return. Come on. This snippet introduces a new kind of permission, the flow permission f. Thank you for that. The f permission is expected whenever an expression uses an input reference like reference string 0, or returns an output reference like return s underscore ref. Unlike the read-write ownership permissions, f does not change throughout the body of a function. A reference has the f permission if it's allowed to be used, that is, to flow in a particular expression. For example, let's say we change first to a new function, first underscore or. that includes a default parameter. I'll admit I actually don't understand what flow means, but I'm going to pretend I do and move forward. Function first or, which takes in a reference to vector with the default and a default of reference string, returning a reference string. If strings dot length is greater than 0, reference strings 0. Or we're returning that. Thank you for that. Else return the default. So it just checks. Yeah, it just checks if the string exists. If not, it returns the default. This function no longer compiles because the expression reference strings and default lack the necessary F permission to be returned. But why? Rust gives the following error: missing lifetime specifier. I wouldn't understand a word of what that means. Expected named lifetime parameter. Here. Help. This function's return type contains a borrowed value, but the signature does not say whether it is borrowed from strings or default. Okay. I feel a crack of an egg here in understanding, but I still don't know what I'm talking about here. The message missing lifetime specifier is a bit mysterious, you think, boy? But the help message provides you some useful context. If Rust just looks at the function signature, it doesn't know whether the output, reference string, is a reference to either strings or default. To understand why that matters, let's say we use first underscore or like this. Function main. Let strings equal vec. Initialize vec, but it's got nothing in it. Let default equal strings from default. Okay, let s equal first or strings and default. Drop default print s. Okay, yeah, that's just terrible coding. You could get either from here. Okay, I think I understand a little bit here. I don't know how to explain it currently. I'm getting some goop out of that egg, you know? This program is unsafe if first underscore or allows default to flow into the return value. Okay, that's what flow means. Like the previous example, drop could invalidate s. Noken. Rust would only allow this program to compile if it was certain that default cannot flow into the return value. Oh, yeah, that's correct. Okay, I think... Okay, yeah. Okay, so because the return... Okay. Oh, it doesn't know whether default or strings was given back. Correct, yeah. That is what it's saying. So, if default could be given back here, a reference to... Sorry, what s is default. That is the reference that is giving back. It is giving the default value. If we drop default, which is not owned by default, then it is attempting to drop s2, which is used later on. Okay. But you could have reasonable behavior as long as your string holds something. So if you have like a person putting in text to a CLI, you put in text in, it passes in, somebody just decides to put no text in, this would error out. This would be a use after free issue, because it would be freed under drop, and then you're using s, which is default. Okay. That makes sense to me. I could understand if it isn't something somebody understands from this explanation, or my explanation, to be honest, how terrible it was. But I think I understand now. This program is unsafe if first or allows default to flow into the return value, like the previous example drop, but invalidate s. Yep, okay. To specify whether default can be returned, Rust provides a mechanism called lifetime parameters. We'll explain that feature later in Chapter 10. We are on Chapter 4. Validating references with lifetime. For now, it's enough to know that 1. Input/output references are treated differently than references within the function body. And 2. Rust uses a different mechanism, F permission, to check the safety of those references. You always check for the F permission. Of course, consent is a very important piece of the puzzle. To see the F permission in another context, say you try to return a reference to a variable on a stack like this. Function, return a string. Returning reference string. Let s equal string from hello world. Let s_ref equal reference s. s_ref. We return that. You just put return here, and it will confuse nobody. No, it will cause no issue. Why? There's no reason for that. Okay. You say you try to return a reference to a variable on the stack like this. Okay, yeah, because s_ref is in the stack after the function ends. At this point, s_ref is no longer within scope and is currently on the stack. The stack is destroyed. The stack frame for return a string is destroyed. sref no longer exists. So we are returning this reference, which no longer exists. We cannot allow it to flow out because it should be destroyed. This program is unsafe because the reference s, will be invalidated when return a string returns. And Rust will reject this program with a symbol similar missing lifetime specifier error. Now, you can understand that error means that s_ref is missing the appropriate flow permissions. That makes sense. Okay. C doesn't do that. It'll just give out garbage memory. And I can see why somebody wouldn't understand why. That makes a lot of sense. I can understand it. You think if I say that makes a lot of sense enough times, people will believe that I know what I'm talking about? Who knows? Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. Thank you, Keith and Nagel. Function, incur, n of type reference to mutable i32. Returning, you could put the word return here. It would hurt nobody. The dereference of n plus 1. Okay? We have main, which lets a mutable n equals 1. Incur, a reference to n. Print line n. Okay. Does this compile? So we have n, which is immutable. We are passing a reference to n. Ownership passes into the function. N inside incur here now owns n, the reference. Now, is this immutable? Oh, okay, they always do this stuff, but they give you a mildly new scenario to try and teach you while also quizzing your knowledge. You kind of have to guess based on the structure. I'm saying these words in order to... Okay, yeah. So, I don't know if this will compile. This is not passing in. Usually it would ask for... Now, I believe the issue here is that we are not passing a reference. Apologies. That's what... Thank you. I'm using a new terminal now because of reason, so I can't actually zoom in. So we would have to pass in a reference to the dereference n in order to get increment to have a mutable reference. Because reference n, I do not believe is writable right now, unless we pass in a reference to the dereferenced n. Do you guys agree? Do you guys think that this will not compile? Because personally, I don't think this will compile due to that issue. Unless I'm thinking about something that's only in vectors. Unless somebody says something else, I'm just going to say that it does not compile. And if I'm wrong, I've lost all trust from the people watching, which is okay with me, honestly. You don't think it will compile either? Silver Sorbet, you're the smartest of anybody here. You're not clear what reference n is? Oh, so reference n is a pointer to n. Yep, it's borrowing n. So reference n is just n. It's like passing an n. So any change here will actually change n here too. So not only are we returning this, the value 2, but we're mutating n itself. Oh, you're not sure on its mutability. Yeah. That's the issue here. So I guess me and Silver agree this shouldn't compile, but we'll learn something either way. Determine whether this program will pass the compiler. If it passes, write the expected output of the program if it were executed. Let mutable s equal a string from hello. Let s2 equal the reference to s. Don't think that's mutable. Let s3 equal a reference to the mutable s. s3 dot push underscore string space world. And then print s2. Okay. I love this question. This brings up so many things. The people who've written this they're fantastic. I'm so glad that they wrote this question. So let's think about flow here. Let's think about permissions flow. I think this is really cool. So S comes in with read, write, and ownership permissions. S2 takes a reference to S, which gives it read and ownership permissions. Okay, that's a good question. Read and ownership permissions are on S2, but not write permissions. Let S3 equal a mutable reference to S. Since S is not owned by S, but instead S2, can we create a reference to something which is not owned? Have I missed something? Did we discuss this? Is that an issue? I don't actually know. I'm going to say it does compile, though. You should not be able to. Okay. You don't think we should be able to? I can understand where you're coming from for that. That would make sense, right? Because it doesn't have ownership. You should not be able to create a ref to something that does not exist. Oh, this exists. This has read permission still. S does exist. It just isn't owned by S. It is owned by S2. I think you can use mute references while immute ref exists. Oh, that's a good point. Can you mix a mutable reference and an immutable reference? Oh, no, I think they explicitly said that. Yeah, you're right. Yeah, yeah, there we go. No, I meant can't. Yeah, I think you're right. You can't mix those two. Yeah, I didn't think about that. You are correct. I am certain on this one. I'll be very surprised if it's not. You can't have a mutable and an immutable reference at the same time. Good stuff. Oh well, big question. Consider this Rust function that pushes a number onto the end of a vector, and then removes and returns the number from the front of the vector. Right, so you got a function which takes in a vector. Uh-oh. Oh no, what? Did I mess up? What are you uh-ohing? Oh no. I'm very concerned now. I'm very concerned, Silver. I'm going to continue on, but know there is fear in my heart. Give and take. Oh, okay, that makes more sense. The delay here really messes me up, man. Alright, so function give and take. We have a v which is brought in of a type vector reference, sorry, a vector I32 reference. N, we also pass in n, which is an I32. We have returned. We push n to the vector. Then we remove the first and we how comfortable it would be if you did. I'm going to do this right now, and I'm going to annoy you guys completely because, like, come on, guys. This is not helpful for anyone, but I'm just gonna. There we go. There's a mic issue. Hello, hello. This is a collection of words. What does the mic? Okay, never mind. It stopped. Okay, I'm gonna try. I'm gonna try reading this with my voice in the background. It's going to be quite difficult. Yeah, you're gonna hear a lot of long pauses, but I gotta see what this mic issue is. Sorry. Maybe if I just do this. Okay. Apologies for that. Audio's good now? Okay, please tell me if there's an issue again. But yes, how hard would this be? How hard would just return b.remote be? Like, come on, look at that. It's so much more readable. Normally, if you try to compile this function, the compiler returns the following error. Error E0596. Anyone read these? Cannot borrow the reference v as mutable, as it is behind a reference. Test.rs function give and take. Oh, consider changing this to be a mutable reference at vector I32. V is a at reference, so the data it refers to cannot be borrowed as mutable. Okay. Yeah, okay, yeah. That makes sense. We're just trying to use something that is not mutable. Assume that the compiler did not reject this function. Select each, if any, of the following programs that could possibly cause undefined behavior if executed. If none of these programs could cause undefined behavior, then click none of these programs? What? Okay. Assume the compiler did not reject this function. Okay, so this function's still in here. Which one of these would cause undefined behavior? Of course, it's multiple selection. Let v equal vec123. Let n equal a reference to v 0, which is 1. Give and take. A reference to v, and we're giving 4. So we're trying to push 4. We're trying to put that'll fail because this is not mutable. Okay, so what does it mean by not reject this function? Does it mean that it's just going to allow you to push this, even though it's not mutable? Even though you're not allowed to push this? I really don't understand what it's trying to do. Does anybody here understand what it's trying to do? What this even means? I'm sorry for that. Let's read the other ones. You think so? You think you understand? Or do you think that this will not error out? That this will do something? I'm going to move forward assuming that this function will work as written without giving errors. That any errors will not be in this this function, but instead in the new code here. Give and take, a reference to v, and 4. So 4 will be at the end. Yeah, that'll fail. That'll fail because it's a reference to the item 0, which is this 1. Yeah, you're correct. So I guess that the only way of reading this would be by assuming this doesn't actually error out. All right, so let's run through this. V is pushed in, N is removed. Sorry, N is pushed to the end, and the first one is removed. Now we go back, and this is not pointing to anything anymore. 0, or the 1 value, is gone. It's dead. It's removed. It's dropped. And now the first one is 2. That doesn't actually update it because we're having a reference to the first element, not having this equal a reference to what would be the first element. So that's going to give undefined behavior. This is a read after free error. Secondarily, let v equals vector 1, 2, 3. Let n equals a reference to 0, give and take. And then we print k, which returns v.remove 0. Okay, I think this will compile and be perfectly fine because n is not accessed. Yeah, as long as this I don't see any issue with this. I don't see any issue with this as long as it actually returns. It'll print 2, 3, 4. I see no issue with that. Lastly, we have v of vec 1, 2, 3. v2 equals a reference to the entirety of v. We take v in, which drops the first one, adds 4 to v. And then we take v2, element 0, and read it. I see no issue with this, because v2 is simply a reference to v. v2 has ownership over v. No, it'll fail. Right, so this is a pointer to v. And in this, v is destroyed because we need to push it. It doesn't have the capacity. We have 3 elements within this array. In order to create an array, a vector, with 4 elements of capacity, we have to destroy the original 3 capacity vector and then create a new 4 capacity vector to put 1, 2, 3, 4 in. At which point, we take v.remove 0, removing the first one, creating a length of 3, but a capacity of 4 vector, and it's still alive. No destruction there. So, this will not work because v is destroyed. It's no longer there, does not exist. Megal agrees. Let's go. I don't see any issue with any of this. See, first question, we're correct, does not compile. Second one, we're correct, does not compile. Thank you, Sorbet. Third question, incorrect. You answered, and it doesn't tell us why. Oh, see the correct answers. I do want to see the correct answer. Okay, so this one is fine. Apparently this one is fine. Why? Why is that one fine? Context. As we saw earlier in the section, v.pushN can cause v to reallocate its internal contents, invalidating any references to the element of v on p. Therefore, calling give and take at v4 causes previously created. I think it's because at v is returned. I think it's because at v is returned. Yeah. At v is returned to nothing. It's not owned. It's not given to any variable. It's returned, but it's not being given to v2. I'm sorry, I just don't understand. Therefore, calling give and take will cause previously created element reference to point to an invalid memory. The 2 programs that bind let n, therefore giving are candidates for undefined behavior. Let v2 Yeah, it does return v0, but that's not relevant. No. The function give and take does not return v0. The function give and take returns v, the entirety of v. But it's not actually caught. There's no variable to get the output. Oh, wait, it has to return an I32, so I guess it would have to return v0? So n equals reference v0, and therefore n can be used later for the final line. v.remove 0 returns v0. Okay, I guess it does. Yeah, it has to, because this is returning an I32, not a vector. But it really doesn't matter because it's not being caught at all. Nothing's taking it in. But yeah, n cannot be used in the file line. This is the correct answer. This is the one that did not. This is the one which gives undefined behavior. This is the only one which is false. This one would not create undefined behavior. That's pretty tricky depending on the return of the function. No, the return of the function is irrelevant. It's not being caught, it's not being used, nothing is returned. Sorry, everything is returned, but it's not being caught. It doesn't actually return to any variable. Returning it doesn't matter. Right. You need to head off. Great stream, great stuff this session, great job. Thank you very much, Magel. I will see you later. I understand where I messed up. This is using v2, not v. I am an idiot. No, I'm not. I still don't understand what's wrong. But thank you for being here. Have a great day, Magel. I wish you the best. I'm going to continue reading now. The two programs will find let n equal reference v0 before give and take are candidates for undefined behavior. Let v2 equal reference v. It's not a candidate because a reference to the container v is not actually invalidated by mutating v. The program that does print line n will cause undefined behavior by reading the invalid memory. The program that does print line k will not cause undefined behavior because it does not use the invalidated reference. Okay? Yeah, I'll admit I don't understand, but I'm not going to hold the rest of us back. I think we're going to end soon anyway. I don't know how far into the next one we can get. Summary. References provide the ability to read and write data without consuming ownership of it. References are created with borrows, at and at mute, and used with the references, dereferences star, often implicitly. However, references can be easily misused. Ross's borrow checker enforces a system of permissions that ensures references are used safely. All variables can read, own, optionally write their data. Creating a reference will transfer permission from the borrowed data to the reference. Permissions are returned once the reference's lifetime has ended. Data must outlive all references to that point. In this section, it probably feels like we've described more of what Rust cannot do than what Rust can do. I disagree. What Rust can do is stop you from doing things that you shouldn't do, and that's what Rust can't do. That is intentional. One of Rust's core features is allowing you to use pointers without garbage collection, while also avoiding undefined behavior. Understanding these safety rules now will help you avoid frustration with the compiler later. Okay. Fixing ownership errors. It looks to me like we are going to go into 3 days on the same chapter. That is fantastic. Learning how to fix an ownership error is a core Rust skill. When the borrow checker rejects your code, how should you respond? In this section, we will discuss several case studies of common ownership errors. Are you still planning on doing Rustlings one day? I very much am. I'm sorry, Silver, for not doing it earlier. I was going to do it last Thursday, but as I discussed, I just haven't had the time. I'm going to try and do it this weekend, however. I really very much want to do it. I'm not entirely sure on that. If you want to join me, I can message you on Lemmy if you drop your Lemmy on there. But again, I can't actually 100% guarantee that I'll be doing it. Sorry about that, Silver. Delta, thank you a lot for giving it to me. I will be doing it eventually. Alright, when the borrow checker rejects your code, how should you respond? In this section? Alright, thanks. We'll discuss several case studies of common ownership errors. Each case study will present a function rejected by the compiler. Then we will explain why Rust rejects the function and show several ways to fix it. The common theme will be understanding whether a function is actually safe or unsafe. Rust will always reject an unsafe program, but sometimes Rust will also reject a safe program. These case studies will show how to respond to errors in both situations. Fixing an unsafe program, returning a reference to the stack. Our first case study is about returning a reference to the stack. Just like we discussed in the last section. And data must outlive all of its references. One moment, apologies. Here's a function we looked at. Function, return a string. We are returning a pointer to a string. Let s equal string from hello world. Return the string. You put the word return here, it would not hurt anybody. When thinking about how to fix this function, we need to ask, why is this program unsafe? Here, the issue is with the lifetime of the reference data. If you want to pass around a reference to a string, you have to make sure that the underlying string lives long enough. Depending on the situation, here are 4 ways you can extend the lifetime of the string. One is to move ownership of the string out of the function, changing reference string to string. Return a string. We're just returning a string, not a reference to string. Let s equal string from hello world. Then we return the value hello world, not a reference. So s is destroyed. The frame within the stack, the frame return a string within the stack is destroyed. S is destroyed, but we do pass back by value s. Another possibility is to return a string literal, which lives forever, indicated by static. This solution applies if we never intend to change the string, and then a heap allocation is unnecessary. Function return a string. Reference to a static string. Then we just return hello world. There. Another possibility is to defer borrow checking to runtime by using garbage collection. For example, you can use a reference counted pointer. Okay? Using from the standard library rc, reference counter. Return a string. Returning a reference counter string. Let s equal rc, new, passing in the string from hello world. rc, clone, s. We are cloning a reference to s and returning it. I didn't know you can make variables live forever. Yeah, it's just a static variable. I'm glad to know that too. We will discuss reference counting more in chapter 15. Wow, guys, you think we're going to get there before everybody just stops coming to these, or I stop doing them? Wow, guys. I hope so. I like talking to you guys. Using standard rc, function return a string, or rc string, let s equal. Oh, we've already done that. Thank you, Keith. I hope to always be here, and I hope to always see you guys here. I love both of you. You guys are fantastic. In short, rc clone only clones a pointer to s, and not the data itself. At runtime, the rc checks when the last rc pointing to data has been dropped. and then deallocates the data. Okay. RC is a kind of garbage collection in of itself. Yet another possibility is to have the caller provide a slot to put the string inside a mutable reference. Okay. Functions return a string. Output equals a mutable reference to a string. Output dot replace range dot dot hello world. Oh, okay, so you give a variable to the function, which is then mutated within the function, and then you use the variable later. I guess to let's just ensure I don't have anything in my history. I use this for work, so I don't want to accidentally put some code that is not mine to show you guys in here. Sorry about that. So if we have main, apologies. We have main, we have let at mute, var equal probably string : from. This is. Then we have return a string. Why is this not? Who cares? And we are putting in var by a mutable reference. This would be the use. You think I use a $sign instead? That is very true. Thank you for that. Too much PHP, guys. Thank you for that. But yeah, I believe. Well, there's no file name. Of course, that's not going to work. But I believe this would be the usage of it. I can see no main issue with this. I don't think this would be an issue at all. This would just create a variable called var with the string this is. It would delete it, replace the range of the entirety of it with hello world. We bring in a variable, which is then passed in, which is then altered, and then we would print it out or do whatever we really want. Here. That's very nice. Thank you. There. See you soon, Sorbet. Honestly, I don't think we're going to be going for much longer. We got 20 minutes on this. First point in which I can kind of stop, I think I might just go towards. This was just for me to be entirely clear, just to show myself exactly what this does. But var would be used within println, however you would use var. Probably like this. And this would output hello world, as we had a slot, a variable, which was then passed in, replaced, and now is used. That way, we extend the lifetime of the string here. I can see a few uses for that. That's good to see. And that's honestly better than this. This is using a library. I prefer not to bring libraries in, if possible. But there's probably a lot more uses for the RC. Real-time collection, or runtime collection. That's what RC means, runtime collection, of course. No, it means reference counted. I don't fully understand what a reference counter is, but we should probably read this at some point. I'm just sticking around a little bit, hopefully to get Sorbet back here, because I'm assuming there's going to be something big coming out, but not much I can do about that. Thank you guys for being here, by the way. I'm glad to have you all. Well, the two of you currently. Magel is currently gone, but it's a lot better than I thought. I thought maybe third, fourth session, there'd be nobody back. But no, we have some pretty dedicated people. Especially you, Keith, who is a lovely man. I love everything about you, Keith Nader. Keith Nader? It's Keith Nader 3K. I keep calling you Keith Nader, but it's Keith Nader. I'm sorry. I'm a failure, honestly. Thank you. Right. I'm just going to continue. Silver will be back soon. With this strategy, the caller is responsible for creating space for the string. This style can be verbose, but it can also be more memory efficient if a caller needs to carefully control when allocation occurs. Yep. Which strategy is most appropriate will depend on your application. The idea is to recognize the root issue underlying the surface level ownership error. How long should my string live? Who should be in charge of deallocating it? Once you have a clear answer to those questions, then it's a matter of changing your API to match. Perfectly fair. Fixing an unsafe fixing an unsafe program. Not enough permissions. Another common issue is trying to mutate read-only data or trying to drop data behind a reference. For example, let's say we try to write a function stringify name with title. This reference is supposed to create a person's full name from a vector of name parts, including an extra title. In a function stringify with name title, we have a name of type vector reference, which is a vector of strings, and we're returning a string. Name dot push. We do not have write access because this is not a mutable vector. Probably shadowing and returning, I guess, is what is my guess of how we're going to deal with it. I assume there are quite a few ways, though. Name, read write, push, string, from, esc. So we are pushing esquire to the string, the bottom of it. We are pushing esquire to the end of the vector, which we cannot do because we do not have write permissions. As you can see here, name has read and ownership, and the reference has read. We do not have write. Let full equal name.join here. And then we return full. Once more, you can put the word return here, and it would hurt nobody. This program is rejected by the borrow checker because name is an immutable reference, but name.push requires the write permission. This program is unsafe because push could invalidate other references to name outside of string underscore name underscore with underscore title, like this. Main lets name equal vec string from Ferris. At first equal reference to name 0. Stringify underscore with name title, and then we are taking a reference to name. Print first. Here is the structure. Let's look. Stack main. Name, Ferris, and first both point to the heap memory Ferris. Sorry, point to nothing, which points to Ferris. Oh wow, that's so helpful. They point to a pointer which points Ferris, because it's pointing to the vector which points to the string Ferris. Okay. Location 2, stringify with name, at name. We have name, which points to the vector, which has one pointer to esquire, one pointer to Ferris and one pointer to esquire in location 2 after it is returned from this function. That's fine. First has no ownership. First has no ownership and is a dead variable. Undefined behavior. Pointer used after its pointee is freed because the vector was destroyed. In this example, a reference first to name 0 is created before calling stringify name with title. The function name.push reallocates the contents of name, which invalidates first causing the print line to read deallocated memory. How do we fix this API? One straightforward solution is to change the type of name from reference vec string of type string to reference mutable vec of type string. Okay, that's fair. This is not a good solution. Functions should not mutate their inputs if the caller would not expect it, which is fair. We should shadow. But this is not a good solution. A person calling stringify name with title probably doesn't expect their vector to be modified by this function. Another function like add title to name might be expected to mutate its input, but not our function. Another option is to take ownership of the name by changing reference vector of type string to vector string. Yep, I guess. Okay, sure. Function stringify name with title, mutable name of type vector string, returning string. But this also is not a good solution. It's very rare for Rust functions to take ownership of heap owning data like vectors and strings. That's a bad idea. This version of stringify with this version of stringify name with title would make the input name unusable. Correct. Which is very annoying to a caller, as we discussed at the beginning of references and borrowing. So, the choice of reference vec is actually a good one, which we do not want to change. Instead, we can change the body of the function. There are many possible fixes, which vary in how much memory they use. One possibility is to use the clone input. One possibility is to clone the input name. Stringify with title, name, vec reference of type string, vec of type string reference, returning string. Let mutable name underscore clone equal name dot clone, taking the value, putting into a new piece of memory, and returning a pointer to it. Name underscore clone dot push. We add esquire to the end of it. Let full equal name dot underscore clone dot join. Join it all together. Then return full. By cloning name, we are allowed to mutate the local copy of the vector. However, the clone copies every string in the input. We can avoid unnecessary copies by adding the suffix later. Okay. Here we have let mutable full equal name dot join. Yep, we're just returning full. Full dot push string esquire returning full. So name is not mutated. We simply take the entirety of the name, join it together with spaces in between, and return the value to full, which is mutable. We then add esquire to the end and return by value full. This solution works because slice join already copies the data in name to the string full. In general, writing Rust functions is a careful balance of asking for the right level of permissions. For this example, it's most idiomatic to only expect the read permission on name. Makes sense. Okay, I wish there was a way to tell what everything expected a lot easier, but I guess it'll tell me when I fuck up. Which of the following is not a valid kind of fix of the issue of returning a stack reference from a function? Oh god, sorry. That was quite a while. We went through quite a bit. But we're on the quiz now, so I guess you'll learn a bit from that. Apologies, I kind of thought you were back already. I really feel bad for that. We should have waited for you. Currently, we are asking, I believe you are even here for this part, not a valid fix for returning a stack reference from a function. Take ownership of the return value. Use a reference counted pointer. That is a solution. Expect a mutable slot from the caller. That is... I'm glad to hear. Thank you, Silver, for being understanding. Expect a mutable slot from the caller. Just create a value, pass the value, a variable, pass a variable in, and then utilize that variable after it's mutated. Then the lifetime of the stack frame. That's what we're doing. No, you can't do that. Yeah, you can take ownership of the return value. That's fine. You can't extend the lifetime of the stack frame. That's not possible. It's dead. I believe. Let's say a programmer tried writing the following function. Award PhD, take again name of type pointer to a string, returning string. Let mutable name equals the dereference to name. Name.pushString PhD. Return name. You can put the word return here. It hurts nobody. The Rust compiler rejects the code on the following error. Cannot move out of name, which is behind a shared reference. Yep. Here. The move is here. The move occurs because name has type string, which does not implement the copy trait. Help. Consider borrowing with the reference to the dereference name. Fair. Given the stated purpose of the function, which of the following would be the most idiomatic way to fix the program? The differences from the function above are highlighted. Okay, the awarded PhD returns a person's name with PhD added to the title. So either A, we go with what the compiler stated, we get a reference to the dereference name, and then we mutate the name and return the name being a reference. That would change name. I don't think that's a good solution. Taking in a mutable reference to string and then simply pushing it. I think that's a bad idea because, again, it mutates name. Taking in a mutable name, changing the name, and then returning the name. Again, I think that's a bad idea. Or lastly, cloning the name, pushing it to the new name. By the way, we are shadowing here. Great stuff. And then returning by value the new name with comma space PhD. I believe this would be the best, unless anybody wants to say anything otherwise, because A, this does not mutate name, which existed before this function arrived. Well, actually, that's really the only thing with this. The first one, I think, is going to error out. But I believe this is the best one, because this simply clones it, and with the new name variable in a new piece of data, puts comma, space, PhD, before returning name. But it doesn't have copy trait, or am I missing something here? It doesn't have the copy trait, but it does have the clone. But it does have access to the clone function. Am I wrong in that? I would likely be missing something here. Do you believe this would error out? I believe this would simply clone it, take the value, and then add it to the name. I could be entirely wrong here. I don't really know. I think I'm going to answer with this, but you may be right, Silver. You are the smartest of us all here, sadly. I am an idiot, but I think I'm going to keep with this, personally. Oh, clone is perfectly fine. Good to hear. Question 3 of 3. Let's say a programmer tried to writing the following function. After these questions, I think we're done for the day. Rounds all the floats in a vector to the nearest integer in place. Function, round in place. Vector of vec, taking a float, 32. A reference to a vector of float 32s. For n in v, for every item in the vector, the dereferenced n equals n dot round. Okay. The Rust compiler rejects their code with the following error. Error. Cannot assign to reference n, which is behind a reference. In here, this iterator yields a reference. So n is a reference. The dereferenced n is the issue. N is a reference. The data it refers to cannot be written. Given the stated purpose of the function, which of the following would be the most idiomatic way to fix the program? Differences from this function are highlighted. Firstly, we return a vector. We return a separate vector of f32 to create a new mutable v2 equals vector : new. For every section in n, we return. For n in v, we return. For n in v, we push to v2 n.round, the rounded item from the vector pushed into v2, the new vector. We then return. You could just put the return word here. It hurts nobody. We return v2, the new vector. I don't believe this is a great one, because it says rounds all the floats in a vector to the nearest integer in place. In place, I assume what that means is that it wants us to mutate. If I'm incorrect on that, then I don't understand the question in and of itself. But if I'm correct, I believe mutating is what is wanted. Function round in place, mutable vector of type vec32. You want to pass in a mutable vector, in which case we can mutate here. That's fine. This will just work as it is. I think this is the best one because it mutates, changing it in place. Round in place, we create for mut n in a clone of v2, n equals n.round. Okay, so we are creating a new mutable v.clone, and for every object in it, we are changing n to n.round. This doesn't actually do anything. It doesn't even return anything. There's no return, and this is a clone instance. I don't believe that this would actually mutate at all. So I don't think that's actually going to do anything. I think that's useless. Am I incorrect on that? I believe that this doesn't do anything. We'll see in the description of why later. Function round in place, taking in v a reference to a mutable vector f32. For n in v, what is the difference between these two? A reference to a mutable vector. Oh, actually, this I believe is what we want. We want the reference to the mutable vector so that we change the vector that is being passed in. I believe that's what we want to do. So unless we're trying to do something funky and I don't understand it, I think this is the correct option because we are trying to mutate the original vector. I'm going to submit the query and see. We were correct. That is not a valid way to fix. Yep. This one, we were correct. Yep, we're allowed to clone. The function is not intended to change someone's original name, so changing the type of name to either a mute string or a string would be inappropriate. The solution proposed by the compiler of reference to a dereferenced name is not sufficient. An acceptable solution is to clone the data with name.clone and mutate the local copy. And this one's correct. Fantastic. Twice in a row, I got it correct twice. That makes me happy. I will sleep well tonight. Right, thirdly, that's great. Context. Because this function is supposed to round a vector in place, it would not be idiomatic to return a new copy of the same vector with returning vector f32, or to consume ownership of the vector, mutable v vec f32. The best solution is to change the type signature from reference vector f32 to reference mute vector f32. Okay, fantastic. Does everybody understand that? Because I think we're about done today. Has everybody enjoyed this day of learning Rust? The second inside of the ownership section of 3, perhaps 4. Has everybody had a good time? Because I believe this is where we're going to end it. Thank you, Keith. I'm glad you enjoyed yourself. I'm glad you guys are still here. Yeah, it was pretty good. I agree. I'm really liking Rust. It's quite confusing. There are some things I'm not fully grasping, but I think it's good. I think that this will stop a lot of issues and errors, and perhaps once I understand it more, it'll be more approachable to me than C code. I can understand why a lot of people going into this field as a new learner would gravitate towards this. You guys like Rust so far? Do you think that Rust is a good language? Do you think this is something that after you understand it more, you're going to stick with, write code for, suggest in industry, or just write for yourself? Or do you think you're just gonna kind of fly by? You think you're gonna learn this enough and just it be another thing that you've done? Because honestly, I think I'm gonna stick with Rust. I quite like it. You're gonna make a few toy apps? I'm glad to hear. Make them open source. Let some people play with them too. You'll need some more practice in order to fully appreciate it. Or sorry, fully understand it. I completely agree. I really don't understand what's going on in a lot of ways. But yeah. On that note, I think I am done. There is, by Magel, a challenge for us. I'm going to do everything in my power, which I still might fail, to do that challenge. I suggest you guys do too, and post about it in the community. I'd love to see you in there. I really heavily suggest that you do finish that challenge. It should be in the announcement for today. Once more, thank you all for being here, but this is where I'm going to leave. Goodbye, everybody. I hope you have a fantastic day. And I'm going to end on that.